So after taking the telescope apart to clean the mirrors, I was next forced with learning how to reassemble it and how to collimate it. I was familiar with the term collinear from my computer-aided design background, but I was not familiar with the term or the process of collimation, which is basically making things collinear. Looking in the internet, there's lots of YouTube videos on the subject, but I still think I have something to add. One is I'm going to talk about my own personal experience, my unique experience. And second, I think I want to look at this thing from my engineering perspective. So let me first define some terminology I'm going to use in this video. First, I'm going to define a coordinate system. There's an axis here is defined by the focuser. And it's almost as if you pictured that focuser level, it's kind of like the x-axis is the azimuth axis and the y-axis is kind of the elevation axis, but it's just rotated a little bit. So for the sake of this video, I'm going to define my x-axis as this axis of the focuser tube, the y-axis as the axis perpendicular to that, and the z-axis as the axis coming out the tube in the optical direction, and in units of light years. So looking at the other end of the telescope, to swing it around here. So the x-axis is just in the same plane. It's in the other direction now because I'm looking from the other end. Y is up and Z is in the direction of the tube. A lot of the videos I see a lot of people making a mistake. What I see people doing is putting something in this focuser and not putting it all the way down and leaving a kind of a wobbly axis. What I find is anything you put in here, whether it's an eyepiece or a tool, make sure you put it all the way down, basically to establish a nice stable plane along the collar. Another way to look at this is in computer-aided design in drawings, we have a thing on drawings called datums. Datums are used to define how to position an object either for manufacturing, for inspection, or assembly. In a case like this, where you have something that's round but not really long, the primary datum, which is labeled A on the drawing here, needs to be a nice flat plane to really establish a nice, firm, stable base for everything else. And secondary datum is B, is the axis itself. Now you would tend to think of that, it's not intuitive, because you tend to think of, well, as I insert this in, first I insert it in, the round part into the hole, that's the axis. Well, that is the axis, but the only way to really make it stable is to insert it all the way down to that collar. Hold it down when I assemble the screws. I see some videos where people complaining about, for example, laser collimators because they're too wobbly, and as they turn the screw, the thing moves. Well, you really got to hold this down tight when you tighten that screw. Let me show you this. I'm going to show a 3-step process, and I'm going to show this with a CAD system to show exactly what I'm doing. So here's a CAD system here. Let me bring up my model. Here's the eyepiece or collimation tool that's looking toward the secondary mirror, and then the light bounces off, and then we have our primary mirror, and it has its axis. So let me define a 3-step process. The very first thing I want to do is position this secondary mirror relative to the focuser. So if I change this dimension here to say something else, I position that basically right in front of the focuser. Now in this direction there's another axis as I move it. So basically I'm positioning that secondary mirror so it's right in front of the focus. So that's step 1. The second step is I want this reflected axis to aim at the spot here, which is the little round donut spot on my primary mirror. So the way I do that is with a CAD command called coincident. I'm going to pick this line and I'm going to make this point, which represents the spot in the center of the primary mirror to make that coincident with the line. That's step 2. If we projected a laser or just looking down the eyepiece, it would bounce off the mirror and would directly see that spot. That's really the second step of collimation. Some people tend to start there, but there's really that first step of positioning the mirror. Okay, the third step is to make these two lines collinear. So here's a command called collinear. There's our collinear command. There's the same word right there. So I'm going to make this axis collinear with that axis. Now there's a collimated telescope. So if I shine a laser through the focuser, it bounces off the secondary mirror, goes right to the primary mirror, bounces straight back, and again it reflects off that mirror right back to the eyepiece, and everything is lined up. So that's what we're trying to do with our telescope. I'm going to use two different tools that I'll show you when they come up. I've 3D printed both of these, and I'll put the links to these STL files in the description of the video, or you can buy them. This thing is called the Cheshire eyepiece, and you can buy those on the internet. This is called a Concenter tool. I'll show you what it's used for, and I'm going to start with that for our step 1. I'm going to take off this. This is actually the adapter from 2" down to 1 1/4. And everything I'm going to do, I'm going to work without this adapter. There's no sense to have, this is the main axis that I'm interested in. There's no sense having an adapter and then something else to have a stack up of tolerance errors. So I'm just going to leave this aside, and all the tools I've designed work on a 2" axis. So we're going to put this in here, but first, as you look down the focuser, it can be very confusing to understand what you're looking at. Things are reflecting back and forth, and it's hard to tell what's what. So let's take things in a logical order, and let me show you a tip that I found that's very useful. What I'm going to do is going to take 2 different colors of stiff paper, and one of them I'm going to put across from the focuser, and then down inside the tube I'm going to put this green stiff paper. So anything that reflects in the secondary mirror, I see the green paper, not the primary mirror. So much clearer what I'm looking at. So first task is just to position the secondary mirror inside here, and I don't want to look at anything else. If you look down inside, you'll see these 3 screws. If you got a telescope from the factory, this is probably done, and it's never going to change until you take it out to clean it. But that was my problem. It was all disassembled, and I had to do this step. So you might not have to do this step. So what I do is hold on to this mirror so it doesn't drop, gradually loosen the center screw, and then adjust these screws together, in or out, to line up that mirror down the z-axis. And it's really important here to make sure as you do this to kind of hold it carefully, because if you back this center screw out too far, it's going to fall off. So I'm going to get back to this later, but there's a thing called the secondary mirror offset. And in my terminology, it's offset in the X direction. And there's a formula I'll show later, but in my case, it wants to be 1.6 millimeter away from the focuser. The way to adjust that X offset is to tighten and loosen these nuts on the other opposite end of that vein of the spider. All right, another axis to orient is if you look at secondary mirror, it's elliptical. Even though when I look on the end, it's round, or look straight from the side, it looks round. It's really elliptical, and I want that elliptical, that major axis to line up with the x-axis of the telescope. So as I rotate that, you can see what it looks like looking down inside. So I'm looking at that through this Concenter tool, and the idea is I've got some round graticles here printed so that I can tell, does that thing look like it's perfectly centered, and does it look like it's round and aligned? Okay, now in the In the Y direction, again, you probably won't have to do this, but I had to check it because I had it completely apart and I have no idea of the history of this telescope before I got it. As you look down in the focuser, in the Y-axis, the way I align that is with the vanes in the other axis. You know, loosen one and tighten the other, you know, to move it in one direction or the other. So at that point, I've now positioned the secondary mirror in the X, Y, and Z positions and in the Z rotation on the axis. Now, most of the videos that I watched ignore this step, and maybe rightfully so, because they assume that's already safely done, it's never been mucked with. But in my experience, I had no idea of the history of this telescope, so I needed to check it. So when I get that done, when I look through this Concenter tool, with that orange and green paper, I can clearly see how well that thing is centered and is it round, meaning that I've got that, you know, axis tilted the right way. All right, so that's the step one. I've got my secondary mirror positioned relative to the focuser tube. The next thing I'm going to do is use a different tool called a Cheshire eyepiece, and it's very similar. The difference is there's kind of a port in the side where if I shine a flashlight in here, I can illuminate this thing, so when the image reflects back, I can see what I'm looking at. In step two, I'm going to look down this thing and make sure I see that center spot in the primary mirror. So I'll center this on here and make sure I've fit it tight against that collar, so it's nice and stable. So another tip I found, it works well, is way down in the bottom on that mirror is a little donut white shape. And I find if I shine a flashlight down here, hold it off to the side so I don't blind myself, and aim my flashlight right at that paper donut, as I look down the Cheshire tool, I see that thing lit up. So that helps. It helps a lot. Just so I want to look at one thing at a time. And this step two here, we're looking at that center of that primary mirror. So again, remember using my axes of X and Y. Notice that one screw is lined up with the focuser. So if I adjust that screw, I'll effectively move this spot in the x-axis. And to move it in the y-axis, I'll use these two screws as a pair and turn them identical but in opposite directions, which will then move the spot in the y direction. Now, about every video I look at talks about all three of these screws as though they're independent, and you're moving it one way, another way, and a third way. I just found it's much more logical to think of this as an XY system. So one screw moves it in the X direction, and the other two screws as a pair moves it in the Y direction. All right, at this point, my primary mirror is now fully positioned in all 6 degrees of motion. X, Y, Z, and rotation about each axis. All right, the third step is really the easiest step. So if I come around at the other end of this, there's 3 different screws. There's actually 2 for each. One unlocks. So I unlock these 3 and then adjust the other one. And then when I'm done, carefully lock them all gradually to bring it in together. And again, notice that this screw here is aligned with that focuser. The telescope is built the way I'm describing it, with an x-axis. So as I adjust that X screw, it's going to move the spot in one X direction, and I use the other 2 as a pair. Well, the other tip I want to point out is when I'm now I'm no longer looking so much at the spot, I'm looking at the reflection back. So it helps a lot to shine a light in the side, and that will light up in this reflection. I see what's lit up is the inside of this Cheshire eyepiece, call it an eyepiece, as reflected back through that whole chain of events, looking down the mirror, reflect off the primary, back off the secondary, and then back, and I see that bright spot. Okay, so what I was saying, this one screw lined up with the focuser will move that spot back and forth in the X direction, and the other two I'll turn as a pair. I'll turn one in and one out the same amount. We'll bring it up and down in the Y direction. Again, I say go for it. If you want to turn all three and watch it move in all three directions, that's fine. But I find this seems much simpler to me to actually move it in the X and Y directions independently by turning the screws this way. So at this point, when I get that all lined up, now the telescope is collimated. And as I look down inside, I see it's kind of hard to see it, but there's the donut way down in the center, and reflected back, I see the inside of that Cheshire eyepiece. All right, a couple tips. One is don't get distracted by the reflected image of these veins you might see. They could be a little bit offset, but that really doesn't matter, because what you're lining up is those two axes. It doesn't really matter even if the whole thing is a little bit off, a fraction of a degree non-parallel to the optical tube or the outer tube of the telescope. So don't worry about that. All right, some of the mistakes I made. The very first thing I did was when I reassembled this, there's three clips that hold the mirror to this assembly, and I thought I'd want to make them pretty tight so the mirror wouldn't wiggle around. But what took me a while to figure out why I couldn't really get a good focus was that I had done what's made pinched optics by tightening those 3 points too tight. I kind of, we actually could bend that mirror a little bit. All right, well, the second mistake that I made was just following some of the videos, just started aligning the secondary mirror, looking at the spot, and then aligning the primary mirror to look back, but I hadn't really considered positioning the secondary mirror, the XYZ position and that actual alignment of that rotation about that Z axis. The other thing I'll get into is being confused by this secondary mirror offset. Some mistakes I've seen in some of the videos, like I said, is that one I fell into of not even considering the position of the secondary mirror before trying to collimate it. And the big one is people not inserting their tool fully down. So basically anything that goes into this focuser should be put all the way down. Now, one exception I found, like if I want to try to focus on something close, like to focus on a tree across the street, I can't quite get this into focus and I have to pull it out. I mean, that could be partly why it's hard to focus on the tree, because the thing gets really wobbly at that point. All right, this topic of the secondary mirror offset, because the view is a cone and the way the light is focused in a cone, one side of this secondary mirror is closer than the other side. And so it doesn't, if the cone comes in with equal angles, it doesn't quite line up. So when you look down inside and do that first step of positioning, this thing called the offset, the Z direction, happens automatically because you're looking at a view that's equal in both directions, and you'll automatically position that mirror with a proper offset to line up with the view. But in the other direction, you can't see it. So the only way to know is to go by this formula that this offset in this x direction is determined by this formula, what they call the secondary size. No, that's the minor axis of the ellipse, divided by 4 times the focal ratio. So the focal ratio of this telescope, that's the primary mirror focal length divided by the aperture, and in this case it's about 5.9, almost f6. So the computed offset for this telescope is 1.6 millimeters. It's a pretty small amount. But what I did then was to measure the distance from the two sides and move that the spider to move this center just about 1.6 millimeters away. So it's the same offset in the x-axis and the z-axis, and it's a very small amount. So it's not going to make a big difference. You're still collated, you still still collimated. You've got the two axes looking at each other. But where this is going to come into play is when you use an eyepiece, I think that uses has a larger optic for a wide angle. It might not be lined up properly with that mirror. And it's also going to come into play, I don't do this, but astrophotography, they want the view to be illuminated uniformly across the mirror. In conclusion, do I know everything at this point? Well, I'm sure absolutely not, but I think I'm learning. Is it perfect? I don't think so. This is I find it hard to do. People say it's easy. I think they're kind of like lying, like what kind of gas mileage they get on their car. But I think I've got it good enough. So thanks for bearing with me. It's a kind of a technical, difficult topic, and I've looked at a lot of videos, and it's easy and it's not easy. Conceptually, it's easy, but it's very difficult, particularly mucking with this secondary mirror, because you've got basically 3 screws in order to align 6 degrees of freedom. So it's very awkward. There's no way around it. Well, anyway, stay curious, keep learning, keep looking up.